Thanks for joining us for today's webinar, Go Small or Go Home, What's Coming in HVAC, with Matthew Shaffer and Andrew Poerschke from IBACOS. My name is Betsy Scott with the Alliance. Before we kick things off today, I just want to thank our sponsors. You can see at the bottom of the screen, and certainly the Department of Energy. A lot of the research work that the guys are going to be talking about today is work that we're doing through the Building America program. So thank you, DOE, and thanks to our sponsors for making today's session possible. So why are we talking about small ducts? As the loads in homes get lower, the volume of conditioned air that's required drops. And we talked about this a bit at the Tech Summit earlier this year. Matthew gave a brief presentation talking about some of the research that we've been doing into smaller diameter systems. There was some good interest from you guys in hearing more about this topic. So both Matthew and Andrew will be sharing several different research projects that we're working on today in a bit more detail. So here is the flow of the agenda of what the guys are going to walk through today. And if you have any follow-up questions, always feel free to email those to me at escott@ibacos.com, and we'll field questions during today's session as well. And then the slides and the recording of today's session will be available on our website following the call. So I'm going to turn the floor over to Matthew.
Great, thanks guys. I guess let's start talking about right sizing, and we can revisit this. We've talked a lot about right sizing in the past with making sure that you actually design your system to meet the loads that your house is at. So I think over the years, builders have become better at this, and they're actually designing the system to meet the load pretty well. But now we have a little bit more of a problem with thermal comfort. The thermal enclosure has increased. It's become better. The space conditioning load has gone down, but we're not sure what that really means to thermal comfort. So if we look at the bar chart on the bottom here, you have a traditional HVAC system, and this is a hypothetical example. But let's say it was a 5-ton air conditioning system. A new home built to current code is closer to 3 tons, but if you build to an IECC 2012 code, the newest code, you're going to be closer to 1.5 tons. So we've seen the system go down by more than 50%. So now the question is, what does that do to thermal comfort? When you were delivering 2,000 CFM of air, you had a lot of air blowing into a room, and you had good turnover in the room and good mixing because you had such a large volume of air. Now there isn't as much air going into the room, so you may not get the mixing you need. What this means is you're basically oversized, or the system you're installing is going to be larger than what you need. So revisiting the right sizing again, lower load means the more the safety adjustments can skew your final result. And I think if we think about this from the perspective of when you had a 5-ton air conditioning system in a house, it didn't really matter what your electronic appliances were because they were a minor part of 5 tons. Now if you're at a 1.5-ton cooling load and you install a lot of electronics in your house, like very large plasma screen TVs, you're going to add around 1,000 BTUH to a house that's already pretty low load. So you don't have as much margin or as much, what would you call that? Margin
like
of error.
Safety
factor.
Safety factor.
Yeah, so the right sizing pays off with lower risk and fewer customer complaints, but you have the problem of your safety margin is now smaller too. The ducts are really important with this as well. Let's say you have a very low load home and you are at 1.5 tons, but you have very large ducts. You're not going to deliver at the right velocity. So what this really means is you have builders need more options to deal with this type of work. So what are the challenges to right sizing? The first is that contractors initially gave a lot of pushback to doing right sizing to start with. But over the years, they've become accustomed to it, and they've come around. And we've seen them, more people are doing the right sizing process with the ACA design. But we're still seeing a little bit of problem with using new types of ducting systems, but because there isn't a lot out there, and it's kind of one of these. We just have to show them the product and then let them educate themselves to make it, to install them into the field. Mm-hmm. So we have a couple of reasons that there's pushback. The contractors, which I just said, they actually can be educated, and they'll come around and start doing the process the right way. The other pushback, and the other problem that we can run into is homeowners will complain that they don't have an air conditioning system that's as big as the neighbors have. So the Joneses have a 5-ton, why do I have a 3-ton? Am I not getting the right value for my money? And what does this mean for comfort? It's the stakes can be pretty high related to comfort. If you have a lot of complaints, then you're going to get a lot of callbacks. So how do you meet the need of the customer in even climates that are hot and humid? Let's say you have a large system in a hot, humid climate like Houston, Texas. If you have short cycling, you aren't going to remove the moisture, and then you're going to have potential for mold growth. So the stakes are pretty high. You're going to have you could have customer complaints, or you could have potential durability issues, and you really don't want either. So one of our solutions that we've been investigating is small diameter ducts. So why are they a good solution? From what we've seen, from the work we've done, they're easier to install because there's less components. There's less number of parts you have to put together, and it's easier to keep them in stock. What this means is you have fewer SKUs. Fewer SKUs mean it's easier to manage your parts in your inventory. So we think that's going to be useful, and it also gives you a lot of leverage for purchasing power. Instead of buying 10 units of 10 parts, you're buying 100 units of one part, and this gives you more ability to buy a large quantity and store them more accurately. Mm-hmm. Smaller ducts are much easier to put into conditioned space. This is important because most of the energy code is trending toward ducts in conditioned space. It's reducing the load on the house, and it's pretty much the right way of doing this. You have less risk issues in a hot, humid climate like the South, again, Houston, where if you have air conditioning ducts in your attic and there's air blowing in from the outside, you could have condensation onto your ducts if they're not well insulated. And another good opportunity is less leakage. If you have less fittings between different types of parts, you're going to have less opportunity for there being a leak. And it's easier to seal consistent parts that are the same size as compared to ducts that keep decreasing in size using your standard pressure regain method. What this really means in the end is you can increase your homeowner's comfort, and this results in fewer callbacks. So you're decreasing your risk. Delivering customer comfort in a low-load home. So really, if you look at the different types of air handlers you can have and the different types of ducts you can have, if you have a small air handler and large ducts, that means, let's say you have a 1.5-ton system, but you're still using your 5-ton duct system. You aren't going to deliver the right velocity into the space, and you're going to end up with an unsatisfied homeowner because the air isn't mixing into the room. It's just kind of falling out of the register and dumping itself into the room. Where a small air handler with smaller ducts works pretty well because you have a nice ventilation and penetration into the room with the air that's diffusing into it. So large ducts with a traditional air handler, let's say that's both a 5-ton air handler and a 5-ton duct design, it's going to short cycle so often in a low-load home that you aren't going to be able to ever remove the humidity, and the noise of the system starting up and shutting down is going to be a problem too. So we've noticed that if you have an air handler that's running for an hour and a half, people aren't going to notice the noise as much because they become somewhat numb to the noise, whereas if the system starts up and shuts down in every 5 minutes, you're going to have a lot more complaints about it. And the traditional air handler with small ducts, it kind of doesn't really make a whole bunch of sense. So we're going to move on and talk about the bad rap of the small ducts. We're just going to knock these down one by one. The rumor is that they are bad at mixing room air under a variable air volume. So we're going to talk about that. We hear that they're inefficient because of their fan watt draw, and we hear that they're noisy. For this presentation, we're going to talk mostly about Unico, and SpacePack is another option. We aren't necessarily endorsing Unico. They offer a product that we think is good and it meets a lot of the requirements, but we are generally talking about thermal comfort in low load homes, and one way of meeting that need is a small diameter duct system, and Unico offers that with a small diameter high velocity duct system, and it works. But they're talking about heat pumps, and they don't have a natural gas furnace option that's associated with this. And actually, there is no low load natural gas furnace on the market right now that's below 40,000 BTUH. So heat pumps are the only thing you have right now for low load homes. But let's talk about the myths that we have that we're gonna deal with. One of the things that I read a long time ago was there's very poor throw with modulation. So basically, what I heard was that if the small diameter high velocity duct system is designed to have 40 CFM at the supply, and you modulated it down to 20 CFM, it wouldn't throw properly because it was a highly engineered nozzle. Actually, it would be called a nozzle if you really think about it in engineering terms, the outlet. What we found after testing is that they actually have very good throw under a wide range of airflows. And the reason for this, I believe, is related to the openness of the diffuser. It's basically a round 2-inch for Unico, and it's a 2.5-inch for other systems that we've looked at. And there's nothing cutting the air coming out of it, so the air kind of sticks together and penetrates very deeply into the room. So here's a test that Andrew completed at the Pittsburgh Lab House. You can see that the photo on the right shows a piece of black felt hanging in front of the air diffuser, and basically you ran this in heating mode.
Yep. Yeah, we ran this in both heating and cooling mode, and basically what we turned the system on kind of in fan-only mode for maybe a 10-minute period to equalize the temperature throughout the room, and then we kicked it on to one of several different air flow rates in both heating and cooling mode, and we used an infrared camera there, and we're able to take pictures and see the progression over time as to how well those particular flow rates were able to get air into the room. And you can see right here we have two different flow rates listed with the same supply air temperature, 20 CFM and 35 CFM. And in both of these cases, you actually get pretty good mixing and pretty good throw all the way to the end of the room. This was a 14-foot room, and so 20 CFM to reach and fully mix a 14-foot room is pretty good. And it's something that you simply couldn't do with a traditional high wall kind of diffuser.
Like a 4x8 diffuser. Yeah. We aren't gonna. We have some other illustrations showing that the air just kind of falls out. So.
We had a question from the audience, you guys, and I think it speaks directly to this issue. So the question is, with the smaller diameter and narrower throw, do you need to add more supplies to each room to ensure full room comfort?
No, you basically add the number of supplies to the room to meet the load, but we have an illustration showing that in a couple more slides, but ultimately what you have is, because you have a long throw, you have more surface area of the air moving into the room, being able to mix with other air in the room. Does that sound right, Andrew?
Yeah, that's exactly what happens. And so you're able, even with a very small number of outlets, you're able to engage the entire amount of room air in order to supply a pretty comfortable room.
Yep. And here's some more empirical measurements we did. This is one we did at our lab here in Pittsburgh. We basically took several diffusers and connected them to a duct blaster and measured the airflow, and then measured the throw using a hot wire anemometer to figure out how far the duct is throwing air into a room until we couldn't measure the velocities below 50 feet per minute. So 50 feet per minute is roughly what you would notice on your skin, and much past that would be considered a draft. So basically 60 feet per minute would be a draft on your body. 50 feet per minute is, for the most part, okay, but it's kind of the lowest tolerance we can measure as well. But what we end up seeing is we have a 4x6 standard supply outlet, or a register, a traditional stamped metal register. We did 2 airflows, one at 20 CFM and one at 40 CFM. And we measured the throw. And they basically, at 20 CFM, it goes about 2 feet, and at 40 CFM, it goes about 4. Whereas we used a small diameter diffuser, and we ran it at 40 CFM and 20 CFM. And under both scenarios, we had throw past 7 feet for sure, and it was measured more accurately at 8 and 10 for 20 and 40 CFM. So that kind of supports the image that we just showed of the black felt test we did at the lab house that Andrew talked about. So and we did this one other way, which pretty much more or less addresses the question that the viewer just asked about mixing in the room. But we were looking at a 10-minute runtime of a standard register versus a 3-inch diameter diffuser in a room in the Pittsburgh. This is a model of the Pittsburgh Lab House master bedroom, and what it basically shows is air is entering the room at about, I think it was entering the room at 60 degrees Fahrenheit. The room was roughly 70 degrees or 80 degrees Fahrenheit from coming back out of a setback. And you can see on the left, the standard register, just basically the air falls out of the register and kind of lands by the door, and it doesn't go into the room very deeply. Whereas the 3-inch diameter diffuser throws clear to the back of the room and actually mixes to all the corners of the room pretty well. So we have 3 different ways that we've looked at the airflow. We measured it at the lab house using a black felt test. We measured it in our laboratory with just basically with a hot wire anemometer and a duct blaster, and then we measured it using CFD analysis, and all of our evidence supports that there's very, very good throw from a small diameter duct, even at very low airflows. So let's go on to the second myth and deal with this one. We've heard before that they're very inefficient due to the high fan watt draw. If you're talking specifically about small diameter high velocity duct systems, they can have very high static pressures. Let's say you're at 1.5 inches, 1.2 inches and above is basically a small diameter high velocity duct system, and at a 1.2 inches of water column, there can be a very high fan watt draw. So when these systems came out, let's say in the 1990s, let's talk about a system in the 1990s. But you had a house that was fairly inefficient for the most part. So and you had a very large airflow. So let's say you're at again, we'll go to the example of 800 CFM. So if you had 800 CFM, you're going to be using a lot of watts to move that air. A new low-load home is closer to 600 to 400
yep.
CFM. So you can have almost, if you're thinking about this comparatively wise to an old system, you can almost have twice as much of a fan watt draw, fan energy consumption as you had previously. And you still aren't going to be inefficient compared to the older system. So it's almost a perspective that it is a large part of the energy consumption, but the load on the home has gone down. So they aren't truly the most efficient, but they aren't inefficient the way people consider them to be. And we've seen them operate at a very, very high performance as far as watts per CFM.
Yeah, we were testing the IBACOS system in the Pittsburgh Lab House, and depending on the flow rate that we were trying to force through the system, we had anywhere from something like 0.2 watts per CFM up to 0.6.
Yep.
But the typical operation range was something closer to a 0.4.
Yep.
So less than half a watt per CFM, which
right.
is in the efficient range.
Yeah, I think old Title 24 code was requiring less than 0.58. So we're even in that range, even under some higher static pressures. So that we haven't noticed this to be a problem when we look at the analysis and we do basically a pie chart of the total energy consumption. It isn't that bad. It's that to write them off as inefficient is an incorrect statement. Myth number 3, we've heard they're loud. I've even talked to people who said before I could even finish talking to them about a small diameter high velocity duct, they said they're loud. And I said, well, have you heard one? They're like, no, it's just loud. So this is just maybe an urban legend. It might have been true years ago with a poorly designed system, but everybody that says that they're loud, it really can't give me an example of it. So, and I haven't measured it either. Like this is an example of a duct in our Pittsburgh lab house, and the system is running and it's on, and it's at 46.6 dBA. And if you turn the system off, the room is basically at 35 dBA. So it isn't creating noise. That's us moving around in the room, and there's a little bit of sound, but it isn't loud by any means. It's even hard to notice that it's running most of the time. So let's go on to some quick questions.
Yeah, we do have a question from the audience. One of the things, it refers kind of back to the slide that you guys just showed. This caller's curious to know what the diffuser or the grill for that kind of system would look like, and what does it contribute to the static pressure?
Yeah, that's a good question. Let's go back a slide and look at this. Yeah, basically it's a round hole. It's an opening. How would you describe that, Andrew?
Yeah, I mean, it's a very smooth outlet. If you can picture, say, for example, water pouring out of just an open pipe or an open faucet or something, it provides very little restriction, relative to for example, a stamped diffuser grill, which does provide some restriction. This kind of outlet basically provides no restriction.
Right.
So an option that they have, if you need to balance the system, you can add a small orifice that pops right in there. It's basically just like a washer that will pop into the outlet, and it actually does add a little bit of static pressure, but the goal of that is to reduce the overall airflow to a given room. So that's actually to be desired at that point.
Yep. Yeah, I think the perception was they're a highly engineered nozzle that has maybe a curvature to it to do some sort of pressure, maybe take advantage of a Venturi effect. But none of the ones that we've seen are highly engineered. They're all pretty straightforward. Good. All right. So we're going to keep going on and talk a little bit about why these why people might want to use these in a production home environment. We're going to talk about a case study from Newtown in Colorado, and then overall we think that there's enough of a need for these that are being talked about in the market that there's probably going to be products coming along soon. There's enough talk in the industry that this is something that's desired. And if you really think about this, the existing duct systems, a sheet metal duct system has been around since Willis Carrier and then early 1900s. So we're due for change. So a research project that Andrew's working on with Building America here is
yeah. So we have a project that we're working on with Newtown Homes in Denver, Colorado, in the Stapleton community. And this is a builder that actually heard about the small diameter duct systems and found it to be very attractive and wanted to try it out in some of their brand new townhome products. One of the current concerns with their townhome products is that the loads are so small, there's not a lot of equipment options out on the market. And so they saw that these small diameter systems are able to provide meet that load in equipment that's designed to be that size. So we're doing a study of a total of 6 different units. I think on the next slide we have a picture of these units. Sorry there. And so we have a kind of a control case, which you can see on the right. There's 3 units, and that will have their traditional ducted system with a gas furnace and a air conditioner, traditionally sized ducts.
Yep.
And then on the left, we have an experiment case where there will be the 2 leftmost units, which are in orange there, have the Unico high-velocity system with a heat pump supplying that load. And then on the right, it is a mini-split ductless heat pump setup. And we'll see a little bit more about the scenario there on the next slide. But these 2 side-by-side houses allow us to really get some good direct comparisons in the exact same climate zone for how well this higher velocity system is performing. And we'll be able to get a much better handle of the efficiency and the comfort differences between these two different systems.
I think it's a pretty good study too, because both of the two different townhomes are oriented the same direction, and they're right next to each other.
Yep.
So they're literally identical.
Mm-hmm.
So the research questions that I think Andrew's really trying to answer here is looking at gas and electric for one.
Yeah. I mean, we're trying to find all electric options for builders, which sometimes can be attractive in these townhome scenarios. But there will be a gas furnace as well, and that's definitely a technology that has been improving as well in the market. There are units that are trying to meet lower and lower loads. And so the one of the other main goals of these homes is simply meeting the Building America Net Zero Energy Home Challenge. And in doing that, these homes will be a HERS 40 in the brand new townhome without PV, and a HERS 10 including PV. So these are going to be highly efficient, high-performing homes. And one of the things that here at IBACOS we're always trying to champion is the idea that you can have energy efficiency and comfort,
right?
And that a well-designed house with a well-designed HVAC system provides both of those, and they go hand in hand, and they aren't exclusive. And so we will be, looking at these homes and how they perform based on a couple of the ASHRAE and ACA standards. And most significantly, what we're looking for is the ability of these systems to keep all of the rooms in the home at a uniform temperature.
Right.
People, they're most likely to complain, I think, about a comfort problem in their home if, say, just one room is uncomfortable. Mm-hmm. And so what we really look at is the overall temperature uniformity in the house and how well any given system is able to provide that uniformity.
And it's interesting too, the ductless heat pump. I've seen them have a lot of problems in the field, because if they're ductless, that means they're really not heating all of the house evenly, because they're not distributing the air. Mm-hmm. Although they do have turning vanes, and they actually modulate the air into the space by turning the vanes of the diffuser. But it's been not uncommon to see that they've had issues with stratification, because it's hard to move the air into a room without a diffuser or without a duct. So what we're likely to see is that the traditional system does a lot of short cycling. That's one thing that we would expect to see. And with short cycling, we might see increased humidity. Mm-hmm. Although in Denver there isn't a lot of humidity, right? But it'll be great to see this when we're done. We'll probably plot this on a psychrometric chart and do the actual ASHRAE 55 comparison.
Yeah, we'll be able to compare humidity from one unit to another, and compare the traditional kind of incumbent system to the newer systems. And it's great to have a set where we have mini-split ductless heat pumps in operation, and we'll really be able to see if in an occupied home with a kind of standard homeowner, how well the systems are able to keep up with the load while minimizing the amount of stratification that might occur.
It's going to be a very neat study. We'll probably be completed at the end of next year.
Yeah, these homes are under construction now, and will be finished in early January.
Okay.
And then we'll monitor them for a year through the remainder of the heating season and basically the entire duration of 2015.
Okay.
So check back in a year for some good results, some good data.
I don't think we have any more questions at this time, so you guys can just keep it rolling here.
Great. We're going to go on to Andrew's study of small diameter self-balancing ducts.
Yeah, so and this is another Building America project which we have been undertaking here actually in our lab at IBACOS, is this self-balancing duct system. So the dream duct system that we can think of is a system which you plug in. It's very simple to plug in. It's like snapping Legos together. Mm-hmm. There's no way to mess it up. And once it's all set up, you're guaranteed to get the airflow you need out of each outlet into each room, kind of regardless of how you snap it together. So with that dream in mind, we've been testing some different concepts that might allow us to get closer to that dream. So standard duct systems require time-intensive balancing and sometimes callbacks, etc., in order to get the required airflow to every room to provide comfort. And so our thought is, what if instead of designing your system in order to supply, say, 50 CFM to one room and 100 CFM to a different room, what if every duct supplied 25 CFM and you instead selected the number of runs that would meet that load? So you might have 2 runs to one room to another room. And that's a much more consistent way to supply the necessary airflow. And so we've started testing the system here in our lab, and these preliminary results do show that the system is able to keep up with that and is able to maintain equivalent airflow out of each duct despite some different scenarios.
Yeah.
And so you can see here's just a quick snapshot from in our lab, some of the testing that we're doing, and you can see on the left here that we've done a case where some of the duct runs are twice as long as the other runs, and even in this case, the airflow is very similar. That we saw a deviation less than 10% between those 2 different duct runs, which the system really is showing a lot of promise. Yeah, and so I just want to talk about some of the advantages of plastic duct systems that would be used for this kind of manifold system. So currently, plastic ducts are not allowed according to code, specifically PVC ductwork. But this is something, PVC ductwork we envision as a great example of how we could use kind of existing building technologies in a new way that perhaps is a better way than some of the incumbent technologies. So you can see in this photo, there's a couple different examples of duct systems. We have the sheet metal steel system. We have a flexible duct system, and then the PVC pipe. And you can see, the PVC pipe has a perfectly smooth interior, and so that actually provides less resistance for the airflow. So even though it's a smaller diameter, you don't have as much of a penalty because you're reducing the internal resistance of the flow. And then if you can imagine how plumbing snaps together, there is 0 leakage in a typical plumbing system. At least that's the goal. And so it's very easy to envision a duct system that's made out of plastic. It doesn't have to be PVC necessarily, but it could be a plastic system very similar to that. And I think it's easy to see a case in which there is minimal leakage out of that. And it's still very easy to snap together. You don't have to worry about adding different sealers and this and that. And it's a pretty straightforward process. So these duct systems are smaller, and we've talked about some of those advantages. It's easier to bring that ductwork into conditioned space. It can run through, for example, interior partition walls much more easily. And if you have to run, say, a bulkhead for some of this ductwork, you're not sacrificing a whole foot or 16 inches of your ceiling for that bulkhead. You might only sacrifice 4 to 8 inches. So it's much easier to bring this ductwork into conditioned space. And quite frankly, it's cheap. PVC pipe is very, very cheap. And if you think about not only the material cost but the labor cost, we think that this is going to be much easier to install, much less time consuming. So we do think that there's going to be a lot of financial benefits actually to going and investigating some of these different options. So here's just a picture of some of the testing we did, again, in our lab home here in Pittsburgh, where we used PVC pipe, actually, in this case, to supply ventilation air to all of the bedrooms. And it worked quite well for that task. And we just kind of wanted to show you this picture to let you know that we've been thinking about this for a while, and that things are in the works to hopefully allow plastic ductwork to be used as such, to we're trying to push towards some code changes that could hopefully allow us to use this plastic duct in the future. Yeah, so just a quick recap on that system we talked about. The system is smaller. We envision this to be able to fit in a floor cavity or a very small bulkhead. And because you're able to bring the ductwork into conditioned space and it's in a centrally located closet or bulkhead, the length of your duct runs can be much, much shorter. So it's a smaller overall system, fewer pieces and parts. Like we talked about before, if you have one 90-degree elbow and one diameter of duct run and a couple of other fittings, you could build an entire system with maybe 5 or 6 different pieces, different SKUs. And that, to somebody who's working at the production scale, that's a very important thing. Instead of having to buy 10 or 20 different fittings and diameters, et cetera, if you only have to buy a couple, it gives you a lot more power. These smoother ducts have less resistance, and so that helps with efficiency. They have zero leakage, which again has many benefits. And this system is frankly compatible with natural gas. And so, in different cases, natural gas is definitely the preferred fuel, and there's no reason that these systems can't be used with that. And these systems are dead easy to install. You could basically have your plumber install all of the ductwork and have everything ready to go. You have your HVAC contractor show up, and in a day hook up your furnace, and you're done. You don't have to have multiple trades in installing the sheet metal ductwork, and there's a lot of potential errors that can happen with traditional duct systems, with flex duct and sheet metal. How many times do you have, for example, runs that aren't fully connected in walls? And a lot of this will be alleviated with, we think, with these plastic duct systems. And frankly, we think they're cheap. Plastic is a very cheap material, and it's also a very effective material. In this case, cheap doesn't mean poor quality. Cheap means more money in your bottom line. So.
Better performance. So it should outperform and be more cost effective. So.
All right. Yeah. So just a quick summary. We think that small diameter ducts can address many of the potential comfort concerns and some of the other problems builders are currently facing trying to integrate HVAC into these low-load homes. These low-load homes do present something of a new challenge. It's not just, sure the load has been reduced by half, so we need a system that's twice as small or that's half as big. But there actually are some new challenges in the way that the load distributions occur. And we're really trying to find solutions for you so that you don't end up having more and more complaints, and so that low-load homes, these efficient homes, we don't want them to get a bad rap.
Right.
We want people to think that they are comfortable, and we want them to be comfortable. So
it's interesting how the energy code is moving toward tighter envelopes and more efficiency, but the occupant comfort isn't part of that equation.
Right.
So.
Right. And so we're really trying to find solutions that allow you to have efficient homes, but that are also very comfortable for the occupants. And the small diameter ductwork solution set currently might be somewhat limited. There's only a couple of companies, but we think that in the future this is an area that could explode with many new options, and so it's an area worth keeping on your radar.
Yeah, we aren't the only people talking about this. We're just part of the. We're just voicing what we see on the landscape of possible opportunities. So.
Yeah, and so again, new products are coming, which should offer various sizes. The dream would be to have both electric and gas options that can meet these lower loads that aren't oversized. And we think that these products are on the roadmap for the future.
And as we look at these new products, we consider them in light of the existing products. And what's undesirable about traditional pressure regain duct systems is that they're highly engineered, and they require to be installed very well. And what we see is the engineering side isn't done every time accurately, because when an HVAC design engineer does the work, he doesn't consider where the trusses are, where the rafters run. So they may make mistakes, and then when it's actually installed in the field, it may not look like the design that the engineer designed. And even if it is exactly as the engineer designed, the craftsmanship may not be to the level that they anticipated. So we know that there's problems on those two fronts. So with this, when we talk to people about the ideal plastic duct system, we consider it in light of these two deficiencies with existing ducts. So I think that pretty much wraps us up. I guess I'm going to turn it back over to Kate or Betsy.
There are a couple of other resources that you can see there that are available to you through other projects that IBACOS has done, one of which is another webinar that was hosted through the Building America program, as well as Matthew's slides from the Tech Summit earlier this year. You'll be able to get these links. Don't worry about trying to write these down. You can get these just by going into the slide deck. They'll be available there for you to click directly and open up and use as you see fit. So thank you guys for taking us through this today. I don't know if there are any other questions.
No more questions right now.
Okay, perfect. Well, thanks for joining us today, and we'll talk to you again soon.
Thanks, guys.
Thank you.